For problem number 8, we first want to make sure we factor both the numerator and the denominator. So we have x plus 5. You got to be really careful here because your answers will depend upon your ability to factor correctly. And so be really, really careful here. Double and triple check. Like multiply out your factors to make sure. X squared minus 3x plus 5x minus 15, good. X squared minus 9, good. Okay, so we got that, and we want to notice here we can cancel those factors. But before we do that, we want to identify the domain of the function, because we're going to reduce this fraction and we're going to lose a factor, but we don't want to forget that we're not allowed to plug in 3 into this function, because 3 causes the denominator to be 0, and we're not allowed to use that. We're not allowed to use 3 in this function. We're not allowed to plug 3 in. So the domain therefore would be all values of x such that x does not equal plus or minus 3. So that's our domain, and we'll get to the range here in a minute. We want to look at the graph of the function before we find the range. So now that we've done that, we're going to go ahead and rewrite the function in its simplest form. So once we have a simplest form, we realize that we can find our vertical, horizontal asymptotes and things like that. But the coordinates of the whole, since we've canceled our x equals 3, or x minus 3 as the factors, we have an x equals 3 as the x coordinate of a whole. And if we replace x with 3 in the factored form and canceled form, we get f of 3 equals negative 3 plus 5. Sorry, I lost my train of thought for a second. So we have 3 plus 5 in the numerator, we have 3 plus 3 in the denominator, and we have 8 over 6, negative 8 over 6, which is negative 4/3. So negative 4/3 then would be the y coordinate of the whole. So we want to get that taken care of, because once we reduce it, sometimes, for me, sometimes I forget to go back and take care of that factor that got canceled. So now that we have determined that the whole and with the whole in the domain, now we can focus on just the factored and reduced version of our function f of x. Our end behavior model is always, we take the most powerful term in the numerator. Don't forget about the minus sign here. Most significant or powerful term in the numerator and denominator, both x. X over x is 1. Minus sign in front means we have y equals negative 1. That's our end behavior model, which is our horizontal asymptote. If our end behavior model is a number, real number, then y equals that real number is our horizontal asymptote. And then x-intercepts. Well, we get an x-intercept when we let y equal 0, which means the numerator of the fraction has to be 0. So if the numerator is 0, the only value that would be at negative 5, because x plus 5 is a factor, so negative 5 would cause the numerator to be 0. And we know that the factor has a multiplicity of 1, so we're going to be crossing the x-axis at negative 5. And how do we find our y-intercept? Well, that x equals 0. So we have negative 5 over 3, which is our y-intercept. If we want to write it in terms of coordinates, that's fine. Vertical asymptote we get when we set the denominator equal to 0 in the reduced version. So we have x equals negative 3. Now let's go ahead and start drawing some of those things here. And do I have a black pen? Yeah. So we have 1, 2, 3, 2, 3, and we're going to draw our vertical asymptote at negative 3. 1, 2, 3. And then we also have our horizontal asymptote of y equals negative 1. We have a hole in the graph when x is equal to 3 and y is equal to negative 4/3. So negative 4/3 is negative 1 1/3. So we have 3 comma negative 4/3 would be somewhere right in there. We don't have to write the coordinates of that hole right there. We already have them here. And then x-intercepts, okay, so we have negative 5. I have an x-intercept there. So we've got everything in place. Oh, did we find a y-intercept? Y-intercept 0, negative 5/3, so that's negative 1 2/3. negative 1 2/3, so somewhere up here, a little bit lower than where the hole is. So you can kind of start seeing what's happening here. We have to move from, on the graph, from this horizontal asymptote to that vertical asymptote, because keep in mind, rational functions are made up of polynomials. Polynomials are continuous for all real numbers. Rational functions are continuous over all real numbers and nice and smooth and sharp points, except for when you have a vertical asymptote or a hole. So again, rational functions domains are all real numbers except for if you have a vertical asymptote or a hole. Any x value that makes the denominator 0 in a rational function is either going to be a vertical asymptote or a hole. So we've already identified the open spaces in our graph, and so we need to just go ahead and draw the graph. I'm going to start a new video for the actual drawing of the graph so that we don't have such a long video.